Okay, here we go. Recording live. I have a soccer ball. It's on the ground. I know I've spoken with this problem before, but you know, it's been a long weekend. The review wouldn't hurt you guys. I have a soccer ball. It's on the ground. I kick it. It's 40 meters a second. Of course, we ignore air friction as always. It's going to be launched at an angle of 30 degrees from the horizontal. Ball goes up, comes down the field. I would like to know how far away the gal should be in order to head it if she can jump up at, say, 2 meters above the ground. How high does it go vertically? The change in elevation is 2. Please note if it came all the way back to the ground, the change in elevation would be 0 because it started on the ground and ended on the ground. This is in the y dimension. If I were a gopher, or playing golf or something like that, and of course I make the shot, then I would say that in the case of golf, that the change in elevation is probably about, I don't know, what, 4 inches? I don't know how deep those little holes are, but we'll say 4 inches, so I'd go minus 4 inches, my change in elevation. My acceleration is going to be minus 9.81. You want to call it 9.8? I don't care, good enough. How long will it be in the air? I don't know. How fast is it going in the vertical direction to start with? Well, it's going at 40 times the sine of 30. Most of us, of course, call that 20. Yes? Okay, question is how did I come up to 40 sine of 30? I did this. I said that this is launching at 40 at a 30-degree angle. The vertical component of that is going to be the opposite leg on our triangle, and the length of this red arrow here is going to be 40 times the sine of 30 degrees. Let me derive that. Sine of 30 degrees, in this case by definition, is going to be the opposite leg over the hypotenuse, which hypotenuse in this case happens to be 40. And if I multiply both sides by the hypotenuse, then it will give me the length of the height of the opposite leg. So in this case, it would be 40 times sine of 30. Sine of 30 is 0.5, so it works out to be 20 anyway. How fast is it going in the downward direction only when it hits the person's head? I don't know. At this point here, I can solve for the amount of time it takes. And the reason I want to find the amount of time is because if I knew how fast it was moving sideways, which of course I do, it's just going to be 40, not the sine of 30, but the cosine. Great. Cosine of 30 degrees. And let's suppose that the 40 of cosine of 30 degrees equals to, or you can punch that in your calculator, figure out what that is. You can just multiply that by the amount of seconds in the air, and there you have it. Because how quickly will it accelerate, excuse me, not with a W, with an R. How quickly does the ball accelerate sideways? Please don't say 9.8. 0, right, because there's no force on it sideways. Gravity's only pulling it sideways, excuse me, downward. We don't deal with air friction here. So the thing is going to be moving sideways at a certain constant velocity multiplied by the time, and it'll tell me how far downstream I should go. So let's see what we can do in the way of t by guessing an equation. Okay, so we guessed an equation. The s is equal to 1/2 at squared plus vit. And by the way, we're doing all this in the y direction, just to distinguish it. Oh, I could have done vf equals vi plus at, and that would have been an okay guess. The problem is I don't know vf, and I don't know t, so I would have quickly found out that wasn't the best equation to guess. Plug and chug at this point here, which would be step 5. I end up 2 above where I started. Half of a minus 9.81. Time in the air, I haven't got a clue. Starting velocity, let's see, that was 40 sine of 30, better known as 20, times t. I'm going to move everything to the same side of the equation, and I personally, through my own personal bias, prefer to have the coefficient in front of my t squared be positive. In other words, I could move the 2 to the right, or I could move everything to the left. But because I'm going to have to do the quadratic equation, I personally don't like dealing with negative numbers there for that a, all over 2a. Just a personal bias. So I'll have 4.9 905, if I did my math correctly. T squared minus 20t plus 2 is equal to 0. Now at this point you could use the quadratic formula to solve it. Minus b plus or minus square root of b squared minus 4ac, sorry, it's all over the square root, all over 2a. Many of you on your TI calculators have Polysolve, a little program there. You may even have one for quadratic formula. Polysolve is basically the same thing, but instead of just doing things at t squared, it'll actually go t to the 99 power. Of course, it'll take a while to solve something like that. You know, go order an espresso from Starbucks, or in my case, Jamba Juice, because I don't do coffee. But the principle is the same. So let me pause here while we solve for t. Okay, if I plug using the quadratic formula, once again, assuming I did my math correctly, you guys will keep me honest, please. I end up with 3.97 seconds, or a tenth of a second. From there, I can just plug it into whatever the sideways velocity is, which I'll do in a moment, but I'd like to discuss what the meaning of these two numbers works out to be. Right here is the elevation at 3.97 seconds. Right here is the elevation at just a tenth of a second. Obviously, we want the one on the way down, as we discussed last week. Okay, let me try it in the x dimension. S, A, T, V, I, V, F. How far sideways? I don't know. There is no acceleration sideways, which means that Vi and Vf by definition have to be the same. That's why A is 0. Time we already found, 3.97. So I'll plug in the same equation. S equals 1/2 A T squared, where this goes bye-bye anyway, to 0, plus Vi times T. So the distance she should go down the field will equal to 3464, Sam? 34.64 times 3.97, where 3464 is the value of 40 times the cosine of 30 degrees. Help us out here, Sam, please. Multiplying together works out to be, nice and loud, 137.52. Now, of course, that's a bit far, seeing as the soccer field is about 100 meters long, roughly. Longest I think it can be is about 120. Be basically the football field plus a bit of the end zone there, and I forget the actual dimensions, but somewhere around there. But that's clearly beyond that. But then again, we are ignoring air friction. 40 meters a second is somewhere in the neighborhood of, I don't know, 85, pushing 90 miles an hour. So take a soccer ball at 85 or so miles an hour. There's a lot of air friction, so it would go significantly less than that. So there's our problem, and we're sticking to it. Can we get a finger count, please? Here's our problem. We have a spider which launches at 2 meters a second. It is jumping down below. I don't know, it's a wolf spider or something like that. Ignoring air friction, which in the case of the spider is ridiculous, but once again, work with me here. It has to fall down an elevation of 3 meters below to the unsuspecting coyote below or something, whatever it's going to bite. So change in elevation is -3. I would like to know how far away from the base of the tree trunk the spider will land. Have fun. All right, let's plug her in and see what we have here. We have that the change in elevation is -3. Acceleration is -9.81. Amount of time the spider's in the air, I don't know. The velocity started with is 2 sine of 40, and because it's downward, or that's to say we're pushing off in the downward direction, negative direction, it's a -1.49. And final velocity in the y direction as it hits, I don't know. If I solve for t by using s equals 1/2 at squared plus vit in the y dimension, let's put the y on there, I end up with t is 0.64 seconds. Question? That would be a problem. 2 times sine of 40 equals, now I get 1.49. I'm in radians. I'm an idiot. I'm an idiot. That will change everything. Oops, that was recording. Oh well. Okay, one of the basic rules is make sure you're in degrees, not radians like I was. Works out to be 0.66 seconds before it hits. And I just plug it into the same equation but in the x dimension. Okay, it works out to be 0.66 seconds. Multiply that by 2 times the cosine of 40, because that was my sideways initial velocity. And apparently we have 1.01 meters. And so what I would do on the test is I'd give you probably plus or minus 1 on that last digit. Actually, you know what? I'd probably give you slightly more than that, maybe anything between 0.99 and 1.03. I'd give maybe plus or minus 2 in that last digit. It's because you had to round off here. Actually, you didn't have to round off. You can keep all the numbers you calculate, and I usually do. Which then meant that we kind of rounded off here. And, you know, so if you round off twice, you know, it could be that it would work out to be slightly more, slightly less than 1.01. So there we go. In theory, half the time we round off, it should go up, half the time it should go down, but it doesn't seem to always work that way. It seems a lot of times that they both round up or they both round down. So that's our story, and we're sticking to it. Can I get a finger count, please? Checking for further understanding. Please give me the speed as the spider lands down on the ground. How fast is the spider going? Just the speed, please. I don't care about the direction for the moment. We'll worry about the direction in a moment. How fast is he actually going? No, speed is not a vector. It's a scalar. There is no direction. So you're not allowed to split it into x and y components. I use the Pythagorean theorem. Sideways, I know I'm moving at 2 cosine of 40 the entire time of the flight. My downward velocity, let's say the velocity final in the downward direction, I can derive from VF equals VI plus AT. Plugging my numbers in, I came up with a minus 7.76. So I square that, plus my VFX squared, square root all that. After adding them together, I came up with 7.91. And my angle, which I didn't ask for, but if I had, would have been the inverse tangent of VFX over VFY. That's to say how many degrees from the vertical. Yes, I could have measured it from the horizontal, just get the complementary angle to it. That would have also been perfectly fine. Just let me know which way you measured your angle. So in this particular case here, theta is equal to, so my math is right, 11.17 degrees from the vertical. That's about as complicated as I can make it. I guess we could throw a graph on there, have you reproduce a graph with the acceleration curves on displacement if I give you velocity. We kind of did that last chapter. And hey, one more question for you. If I throw a ball straight up from my hand, and we'll say that G, just keep the number simple, is minus 10 instead of minus 9.81. If it left my hand at 30 meters a second, 1 second later, how fast is it going upward? See, is it slowed down by 10? All together, please. 20, great. 1 second after that, how fast is it going? 10. Okay, well, then 1 second later, it should get to the top, yeah? Great. 1 second before it reaches the top, how fast is it going? And what's the acceleration at that point? Negative 10 meters per second squared. I see. What's the acceleration at the top? For just a moment, just a brief moment in time. Okay, how many of you go 0? How many go something other than 0? How many are not sure what I'm asking? How many just flat out don't know? How many don't know how to raise their hand? That's kind of a dumb question. It's like, are you asleep? What's the velocity at the top? That is 0. Well, if the acceleration was also 0, it's not moving and it's not accelerating, it's not going anywhere. That means you'd throw it up there and it would just kind of like stay up there in the middle of the air, just kind of come back next week, grab it out of the air, which would be kind of cool, but you know, certainly not the laws of physics. The acceleration of gravity is constant. It's at minus 9.81 or 10 in our particular case for our example, the entire time of the flight, while it's going up, while it's at the top, while it's going down. As long as you're not holding it, it's in, quote, free fall. It's in free fall even while it's going up, which is why Superman, in my opinion, used to be one of the greatest rides ever invented at Magic Mountain. You've got this little section here where you're actually kind of going through a circle bit. Back here is where you know, they launch and you get thrown way back to the back of your car. Actually, you don't get thrown back. You stay still, the car moves towards you. Actually, your head stays still, your bahunkus and your back get thrown forward, and your neck says, hey, by the way, son, you want to come? That's what happens. At first, I was kind of mad that they wouldn't let me film on it, and then because I'd never ridden it before. You know, so I had to put my video camera down. I wanted to do it, of course, for physics. And you know, as soon as you launch, it's like, you know, get thrown right back. I'm glad they didn't let me do it. I would come out with a black eye or something. You know, that'd ruin your whole day. But once you hit the vertical part here, this section in here, the only force on you is gravity, wheel friction on the cart, and I guess air friction. That's it. Which compared to the force of gravity is pretty much trivial. You are falling while you're going up. That's to say you're in free fall. You are, quote, weightless. Well, you're not really weightless, but you feel weightless because of what we'll hit in Chapter 4, which I'll have to wait to explain normal forces to you. But just real briefly, you don't have your bahunkus trying to become one with your head, trying to squash you on down, and your liver and your small intestines and everything else getting in the way of, you know, everything becoming squashed. And they're allowed to just kind of expand out, and that's why you get the butterflies, if that happens quickly. But when we go on this at Magic Mountain, what you can do is, you know, sneak a marshmallow or something like that on, and you'll see that it floats the entire time. I personally would never advocate bringing a small bottle of water with a little pop dispenser thing and squirting a few drops of water out and just kind of like watching it float through the air. I would never advocate such a thing, though I'd heard rumors that it has been done.